Okay, so we're going to talk and review for our test and go over chemical reactions. Let me grab my pen. Here we go. Okay, so one of the first things is you can have a physical or chemical change. We're going to look at chemical change right now. They both involve energy, though. So actually, let's look at a physical change real quickly. We haven't looked at one in a while. Okay, so even physical changes involve energy. First of all, going from a gas to a solid, this is a physical change. This is deposition. Okay, this is like frost on your windshield. Right, you have gaseous water vapor in the air, really cold day, hits that ice cold windshield, turns into a solid, and releases that extra energy. Right, gases have a lot of energy and a lot of entropy. We'll talk about that. Okay, so deposition, this is a physical change because the composition isn't changing, H2O, H2O. And this is an exothermic change. It's exothermic because energy is a product. Energy is being released. Also, you can tell because gases are going really fast, solids are slow. It lost energy. You can literally see it in the equation. But if that wasn't even there, going from a gas to a solid is slowing down. It's losing energy, exothermic. Okay. Now, we're going to take a look at a chemical change now. Let's say that's a solid. And let's do this. And whatever's left. I'm not balancing this correctly, but that's okay. Okay, I'm not going to balance it right now, but okay, and let's say let's do this. Let's do barf. Okay, so first of all, this is a chemical change, and this is a decomposition. I have one reactant breaking down into multiple pieces. So know your 5. This one happens to be decomposition. Also, we can figure out where the energy would go. We have one thing, breaking its bonds. When you break bonds, energy is absorbed. Right? That's what BARF stands for. Remember, when you form bonds, energy is released. But in this case, we're just breaking bonds on this side. So you're breaking that up. So energy is absorbed. Energy would go on the reactant side. So this is endothermic. Whenever energy is on the reactant side, it's endothermic. That's one thing I kept seeing. So know your sides. Energy is being absorbed in as a reactant, endothermic. Okay, another thing, entropy. Let me get rid of this now. Entropy and energy are two separate ideas. In terms of entropy is disorder. Somebody said entropy was a disease on their lab. Entropy is not a disease. No, it's not. Entropy is disorder. I thought that was an interesting definition. Okay? Entropy is disorder, randomness. And you look at the states of matter. Right? We have solid here. That's very organized. But we do have a gas here and a liquid here. This side is more disordered. This side has higher entropy. Okay? So the product side in this case, and this is something that I saw incorrect on the labs, the product side had more entropy because you're going from something like a solid, very organized, not only into multiple pieces makes it more disorganized, but specifically you have a gas as a product, and we know gases have the most entropy. Okay, so those were some of the big problems I saw with that part of the lab when you guys were analyzing equations. It had to do with energy and entropy that people were getting things wrong. Also, make sure you're memorizing your 5 types. Some people got, they weren't labeling them correctly. Okay, now the other big thing I saw was interpreting the diagrams. So let's go ahead and do that. Okay, so let's say this is 20. Let's say this is 40. And let's say this is 70. And this is potential energy. It's measured in kilojoules. And we're just going to go through and label it. I'm going to just label it briefly. Reactants, products. Always label first. It's going to make your life easier when you have to answer the questions. Look, label the diagram. This is your activated complex, right? We don't really care about that so much, right? That's that in-between state. That's like when you don't have just a reactant, when it goes in between, when it's sort of that, it's not a reactant, it's not a product, it's literally in between the two before it turns back into a product. Okay, so reactant to product. The difference between those is your delta H, your heat of reaction. One main thing I saw over and over, people were doing this backwards. It's products minus reactants. In science in general, when you take a difference, it's usually final minus initial. Right? Products minus reactants. It's usually in reverse. People kept doing it in that order. Products minus reactants. Okay, the other thing I saw a lot of errors on, you go from the reactant up to the top of the hill, that amount is your activation energy. So your activation energy is from the top, your activated complex, minus your reactants. That was a big thing. People kept saying the activation energy was 70, right? Well, it's not. In this case, the activation energy is 70 minus 20. Right? 70 minus 20 is 50 kilojoules. Okay. And what if I don't add 50? This was a big question that people had trouble with. What if I only add 30? Am I going to get up the hill? No reaction. You have to add at least 50 to get over, to have that minimum energy required to get past the transition state. If you don't add at least 50, no reaction happens. It's like if I don't add enough oomph, this is going to just stay a reactant. Okay? Now, what if I add 100? Well, 20 plus 100, that's plenty of energy to get over the hill. You can add more than the required energy, but this is the minimum energy. The activation energy is your minimum energy required. Let's go back to our heat of reaction. If it's product, the products are 40. Go back to blue. 40 minus the reactant is 20. Heat of reaction must have a sign. You're going to find that out in today's assignment. 40 minus 20 is positive 20. Positive. You have to have a sign for heat of reaction. And then I go back to the graph. Positive 20. Was it going up overall? Yeah, it was. Positive 20 overall going up means endothermic. You have to have the sign because the sign tells us it's endothermic. That's why you can't just write it as a regular number. And that's for heat of reaction only. So those were the main things, again, I saw as far as errors with the activation energy and the heat of reaction. So hopefully you guys can make some corrections on that today as you practice. Okay, that's all.